So it's like I always say, don't be a dork, learn about torque. Check it out. This is why things angularly accelerate. When there is a torque, stuff will begin to rotate or stop rotating. Just like when there is a what? When there's a what? There's a what? Just like when there's a force, things will begin to accelerate in a linear fashion. Let's see, we'll color this bolt in like this here. I'll give you a big red dot at the middle of the bolt. And the idea is I could apply a force in two different places on this wrench right here in order to turn that bolt. I could apply a force right here, and then my force in order to loosen the wrench would have to be really big. So here's, let's call this force 2. Or I could apply a force way out here, and you probably have a sense for that already, and this force would be actually quite a bit smaller if the bolt were stuck in the same way. We could call that F1. And these can be distinguished, these two forces can be distinguished by the distance that they are away from the axis of rotation. So we got to label that sucker. In fact, for every problem, identifying the axis of rotation is super, super important. So this distance between the axis of rotation and where the force is applied, I'm going to call ARA. So I'll call this one ARA2, and it's actually a vector pointing from the axis of rotation to where the force is applied. And this other one, well, I guess I'm going to have to use a different color because it's getting a little bit crowded in here. I'm going to say this one, going from here to here, is ARA1. And something must be the same. The stickiness of the bolt or something must be the same between F2 and R2 and F1 and R1. Notice you can either have a large distance out and a small force, or you can have a small distance out and a large force. So we identify this quantity that is constant. We'll call it a loosening quantity for our particular situation of this wrench. Of course, it's going to be a very general thing. The constant quantity is torque. And it's also a vector. The equation for torque that we're going to use, torque is a vector that is R cross F. Interesting. It's a cross product, and you'll remember that cross product means it's going to be the magnitude of R times the magnitude of F times, well, let's see, the dot product. Let's do a little bit of a side here, up in this corner. You remember that a dot product is, for instance, work is F dot D, and you remember that that was F times D times cosine of the angle between F and D. So we're probably not going to use cosine. It probably has something to do with the sine of the angle. Force, the distance out from the axis of rotation times the force times the sine of the angle between them. Notice the angle between ARA and F. If I bring F2 down here, you see the angle between ARA and F is 90 degrees, and the sine of 90 is 1, so that's cool. And over here we've got ARA1 and F1. If I grab F1 and set it down right here, a little phantom F1 right here, then the angle between R1 and F1 is also 90 degrees. So I've got maximum torque. That's because I know how to use a wrench. When you're using a wrench, you don't apply a force like this on the wrench. It will not rotate the bolt. You apply a force directly normal to the wrench in order to cause the bolt to rotate. So that's what the sine of theta is saying. It's saying you'd better keep the angle between ARA and the force at 90 degrees if you want maximum torque. So let's go a step further. Oh, well, first of all, it's got units of, let's see, the units of torque are Newton meters. We've got units of force and units of distance, and they're multiplied by each other. So we can define a couple more things. We can define, since we know that this is what torque is, let's see, the direction, for instance, is given by the right-hand rule. So it's going to be R cross F. We'll take R2 and F2, I'm going to cross. And what I do is use the right-hand rule. I cross R2 into F2, and I find that the direction of this torque is upward. In fact, upward torque loosens bolts, and downward torque, this way, tightens bolts. So what you heard, righty-tighty, lefty-loosey, was really just telling you the direction of the torque. The vector direction of torque is not super important at this point in your physics career, but we do need to know that this, a force this direction, will cause theta to increase. Remember, we can define theta off of any point right here. We'll say that that's the angle theta. If theta is increasing, then we've got a positive angular acceleration, or alpha. And if theta is decreasing with a force that direction, a torque that's into the page would cause theta to decrease, and it would cause an angular acceleration that's negative, or into the page. So the full vector equation is really lovely, but would you please agree that a force this direction, a force out, or a force in would cause absolutely no torque at all? Good. That equation tells you that. Now I want to talk a little bit about a moment arm. So you can also define torque like this. Since torque is R times F times sine of theta, it's also equal to F times R sine theta. And if I look at this picture, I'm going to make this further cluttered, but because you've already taken notes on the original picture, you can handle this. Look at what I've got here. I want to find out what R times sine of theta might be. And I'm going to make a triangle. And my first try is to make a triangle. Let's see, we've got force and we've got R. I want to find out how much. No, we're going to have to be more careful. Let's make another bolt to open here and another wrench. And let's establish that our force is not in those pleasant directions. Let's say our force is actually this way. There's our force, and here's our vector ara. Probably draw it in a different color for you. Ara goes like this. Ooh, I've switched the colors of F and R. Yuck. So there's ara vector and F vector. Notice that if I want to find how much ara is in the direction, how much ara is in the direction of the force, I put some dotted lines down here, and I say, well, the angle theta is the angle between F and ara. So here's theta right here. This is theta. Oh, look, it's already labeled. Theta right there. This is the angle between F and ara. You know what? Yeah, okay. So that's theta, and that means that this is also theta right there. Check to make sure that you believe me. Is this also theta if that's theta? I hope so. So this component right here is ara times sine of theta. This is called the moment arm, and I'm going to write it F times R perp. The moment arm is the distance out from a line of force. You see, it doesn't matter where this force is. It could have been down here. If the wrench were pointed a different direction, it would be as if we were choking up on the wrench instead of just applying a force at the end of the wrench. So let me say that one more time, because this analogy I think is very important. If we're choking up on a wrench like this, that's the same as applying a force at a weird angle at the end of the wrench. So we can define this quantity called R perp and see that torque is F times R perp, or the moment arm. Let me put that word on there. This has something to do with moment of inertia, doesn't it? Yeah, I kind of think it does. Okay, and we could also look at it in terms of F perp. We want the force to be normal to the distance out, so we could resolve this force. Oh man, I'm gonna need another color to do that. I'm gonna have to be very careful. Notice that I could take this force and find out how much of the force is at a right angle to the distance. And that's this over here, right? This is F perp, or F times sine of theta. I hope that nobody's surprised if I continue to write that torque is Fr sine theta. So torque is, well, I guess it's R times F sine theta. And we can identify F sine theta, look at this, F sine theta is F perp. So we can also say that torque is R times F perp, or the force that is normal to the distance out. Wow, that's a messy slide. All right, let's keep going. I want to write down a couple conventions for torque. We should certainly note that if torque is greater than 0, then angular acceleration will be greater than 0, and if torque is less than 0, then angular acceleration will be less than 0. I don't think you're going to be too surprised by that. This is a counterclockwise rotation that will be caused, and this is a clockwise rotation caused by that kind of a torque. And then let's do a little bit of math. Huh? Let's get into it. So Newton's got this. So Newton's swinging around an apple on a string. So here he's grabbed the string, and the apple comes out here like this, and it is red. It is a mass on a string, and he's swinging it around, and it's going in a circle. So somehow he's exerting this force on it. There's a distance r here, and he's exerting a force this direction. That's the force that Newton is exerting on the apple. And the apple, because there's a force in the direction that the apple is able to go, there will be an acceleration. So we can write that the acceleration of the apple is that force divided by the mass of the apple in a very linear fashion, and everything's okay. But I want you to recall that angular acceleration is just linear acceleration divided by r. This comes from the equation that says a is r alpha. We had a whole bunch of these equations. And I want to plug this in over here. We're going to take this and plug it into there. I'm going to have alpha equals acceleration divided by radius, which is force divided by m times r. Interesting. Would you agree that I can multiply by 1? I'm going to multiply by 1 written like this. r divided by r. Okay, so we've got f times r divided by mr squared. Oh boy. Notice that our angle here is 90 degrees. So we won't expect any signs in our torque equation. In fact, F times r can be identified as torque. So we make a concluding pink here. Torque divided by, mr squared. That reminds me of the moment of inertia of a mass on a string. A single mass on a string. Let's say the mass is mass m. A single mass on a string of length r has a moment of inertia of mr squared. So this is actually I. And we can write finally what we just concluded, that angular acceleration is torque times I. Watch this. Watch this. We have just derived a beautiful equation, and I want to contrast it with this one for you. We have initially, here's another one. Look at that. Look at that. Ooh, they're right there. We got A equals F over m. And you know there's more stuff to dress this up, right? We know that acceleration is a vector, and we know that force is a vector, and we know there's a net force. This is Newton's second law. We also know now that angular acceleration is a vector, and torque is a vector, and we need to divide by angular inertia, and we need the net torque. So here are our two equations. These are Newton's second law in linear and angular form. And I want you to see how fantastically similar they are. Torque causes angular acceleration. For a given torque, if the moment of inertia is big, then the angular acceleration will be small. And if the moment of inertia is small, then the angular acceleration will be big. Just like for a given force, acceleration will be big if you have a small mass, and acceleration will be small if you have a big mass. Okay, I don't think there are any surprises right there. So perhaps writing it in one final form, let's see, net torque causes, well, I guess it's I times alpha. Net torque causes acceleration linearly. And we can just make a little summary over here. Linear and angular. We've made a few of these tables. But the linear analog to mass is the linear, and the angular is moment of inertia, or rotational inertia. And the linear alpha goes over to the angular, linear A goes over to angular alpha, and then, of course, force is analog in circles is torque. Okay, here's a cute little challenge for you. I want you to consider two possibilities. There's a pulley here with this rod going through it, and it's on a stand on the ground, and yeah, the ground's really wide, and there's another one over here. Pulley on a stand with a rod going through it. And one of them has masses at the edge, here and here. And each of the masses is m, and there's this other thing wound around it, where there's this heavy mass right here. Let's call it, I don't know, 10m or something. I don't even care what the numbers are going to be, but this is much heavier. The second setup has these guys choked up a little bit. They are still m and m, trying to make them the same size, but this guy coming over here is still 10m, and I want to ask which 10m hits ground first. All right, and I will leave that to you. So it's like I always say, don't be a dork, learn about torque. Check it out. This is why things angularly accelerate. When there is a torque, stuff will begin to rotate or stop rotating. I could apply a force in two different places on this wrench right here in order to turn that bolt. I could apply a force right here, and then my force, in order to loosen the wrench, would have to be really big. So here's, let's call this force 2. Or I could apply a force way out here, and you probably have a sense for that already, and this force would be actually quite a bit smaller if the bolt were stuck in the same way. We could call that F1. And these can be distinguished, these two forces can be distinguished by the distance that they are away from. Just like when there is a what? When there's a what? There's a what? Just like when there's a force, things will begin to accelerate in a linear fashion. Let's see, we'll color this bolt in like this here. I'll give you a big red dot at the middle of the bolt. And the idea is from the axis of rotation. So we got to label that sucker. In fact, for every problem, identifying the axis of rotation is super, super important. So this distance between the axis of rotation and where the force is applied, I'm going to call ara. So I'll call this one